Welcome back, everybody. So now it's another thing that we left untied from a few weeks ago, which was the definition of cardinals. And this is what we had by then. We had this definition. So we said that a set is a cardinal if it's transitive, the belongs relation as a binary relation inside a set is linear, meaning like a linear ordering, and for every member of K, the member X is not equinumerous to K. So these are the three properties that we had. Okay, so according to regularity, the regularity axiom tells us that there is no descending sequence according to the belongs relation ever. There is no descending sequence according to the belong relations ever anywhere. Okay, so this thing up here is equivalent to saying that the belongs relation, I guess restricted to K, well orders. What we are saying is that K is an ordinal. So that's what we said before. We could have put well ordered there. I guess by then we didn't know what well orders were, but we could have just say well orders, or we could just say an ordinal. So first two lines just say K is an ordinal, and the last line says that every X that belongs to K that also must be an ordinal cannot be equinumerous to it. So they all have smaller size. So that's what that's saying, right? So this one is saying that K is the least of all the ordinals alpha such that they are equinumerous to K. Right, so there are many ordinals that have the same cardinality, right? Also, the cardinality of alpha is the same as the cardinality of alpha plus 1. If you put them two together, alpha plus alpha times alpha, they all have the same cardinality. So there are many ordinals with the same cardinality. So among all the ones which have a fixed cardinality, what this is saying is that K is the least one, right? Is no all its members have smaller cardinality, right? Recall that X belongs to K implies that X is a subset of K. So this implies the cardinality of X is less than or equal cardinality of K. And if they are not equinumerous, these two imply that the cardinality of X is strictly less cardinality of K. So all its members have strictly less cardinality. So K is the least one among all those. And then, so by then I said, okay, so here's a definition. We know what the words mean, but it was hard to visualize what it means because we didn't know what ordinals were. So forget about visualizing what it means for now. What's important about this definition is the following theorem that now we can prove. That is that for every set A, there is a unique cardinal, and by cardinal we mean something satisfying this property, that is equinumerous to K. We can prove this now. And then, so we said this is important because this is what we wanted, right? So that means that for each possible size, for each cardinality, there is a unique representative for it, which is a unique thing with this property, satisfies it, so we could use this representative as a member, as a representative for the whole size, for the whole cardinality. The cardinal is, we use it as a name essentially for that size. So now we can prove this thing. So how do we show? Well, we know there is a cardinal, there is an ordinal with size A, right? So how do we do that? So let R be by the well ordering principle, the axiom of choice. Every set has a well ordering. Let alpha be the epsilon image of this well ordering AR, which we know, well, the epsilon image is given by this bijection E. So we have that alpha is equinumerous to E. So there is A. So there is well ordering, an ordinal equinumerous to A. Now, once we know there is one, now we can let K be the least ordinal equinumerous 2A. So once we know there is one, just take the list. Every set of ordinals, every not empty set of ordinals has a list element. And if you're the list, you must also satisfy this property that all your members are actually properly smaller. Okay, so essentially that's what we are doing with these cardinals. I guess one picture that one can draw is if you draw the ordinals look like 0, 1, 2, ... Up here we have omega, omega plus 1, omega plus omega, and then if you go far, you get something called omega 1, which is non-countable. You continue going up, and then you get something called omega 2. So essentially, all of these guys, the finite ones, are all cardinals because they are all finite, and then you get omega is a cardinal, and then all of these guys are countable. So there are a lot of countable ordinals, but then only the least one is going to be the one that is considered a cardinal, and then after that comes the first non-countable ordinal, and that one is called omega 1. This is uncountable. And I guess there are a bunch of them that they are all like equinumerous to each other, omega 1 plus 1, omega 1 plus 2. And then there is a first one that has a larger size, right? So every time we fix a size, there are many that have the same size, but then eventually you reach one that has a strictly larger size. And those red ones are the cardinals. The cardinals are kind of the first ones to have a new size. And this is the way we represent the cardinals in that is unique way. Cool. See you guys in the next video.